Click next line again. Now the insertion pointer is on the third line of main, which looks like this. Rabbits equals count rabbits. This third line of main is called a function call. And I have a choice to click next line. You can either tell the computer to perform only what's inside this function without stopping on each line for you to see, or you can step into it and see the individual lines. Click the first button from the left, then call step into, which shows the squares. And an arrow going from the left between them. Or press Shift F7. Let's see, that sounds familiar. Let's see. Now before step, okay. Normally we use the next line button by default and choose the step into, but only when we specifically want to go into a function. The reason is, okay. It's time to see how those debugging features work. The following procedure takes you through the debugging process. I'm going to skip that part. I'm going to skip the stuff about the Chapter 3. Stopping and inspecting your code. In this chapter, setting, enabling, and disabling breakpoints, typically setting or disabling a breakpoint, inspecting a variable, watching all the local variables, watching any variable. Sometimes things break. But what we're talking about here is the code. Now this is one of those instances when a word or phrase has lots of different meanings. Programmers talk about breaking the code. This phrase usually means one of two things. It may mean that the programmer made a mistake and the code no longer works, but in this chapter we're using a different definition for the term. When you're debugging an application, you can have the application run until it gets to a certain line in the code. The debugger then stops at that line, and you can look at the values of variables, inspect the code, or even change the variables. When the application stops, that's called breaking. The reason it stops on the particular line is because you put a breakpoint on that line. In this chapter, we will talk about setting and manipulating breakpoints in your code if nothing else in your code is broken, and inspecting and modifying various aspects of your code, such as variables, after your code stops at a breakpoint. Tip: in the examples in this chapter, we use a debugger supplied with the CodeBox IDE. If you use a different product, the debugger will probably work about the same, but not precisely the same. For example, everything we show you how to do here you can do in Microsoft Visual C++. The keystrokes and the mouse clicks may be different, but the features are present. Make sure you check the vendor documentation for precise details on using your debugger. To work through the examples in this chapter, make sure that you compile with debug information turned on. In CodeBox, you can compile with debug information by choosing debug in the build target field. Oh, hi, Natalia Loveword, or a Loveword. Thank you so much. Hi, Nicholas. I do read the Bible, just not for publicly. That's more of my personal walk with God sort of thing. When you are developing software, you should always have debug information on. That way, you're always reading to debug your code and fix things. Only when you're ready to release the product formally should you recompile it without debugging information. We do recommend doing a full test of the software again without debug information just to make sure that it still functions correctly. Setting and disabling breakpoints. A breakpoint is a place in your code where you tell the debugger to stop. In the sections that follow, we talk about breakpoints. Please use the breakpoint sample code shown in Lesson 3-1 for these sections. Remember what you're supposed to do. Make sure that you compile it with debug information on. So I'm not going to go through all of this because I'm not using their code blocks because this is a review for me and I already have familiarity doing debugging with other things, including what they were mentioning about the video. Sorry, the visual. Okay, let's see. Shridar Arc. Hi, good morning to you. More like good evening to me, but it is what it is. As far as the other part, I'm sorry, I'm not really sure what that language is, and I don't have a translation readily available. Okay, we'll just run through what they say, but I'm not like going to spend a lot of time showing pictures, etc. Oh, just a heads up, if anything ends up being held for review, it's going to stay that way. And that means I'm not going to see it. So if that was you who made that go to held review, I don't know what you're saying yes or no to. That's how that works. Setting a breakpoint in code blocks. Go ahead and compile the application in Listing 3-1 with debug information turned on. Look at the left margin of the window to the right of the line numbers. Figure 3-1 shows a small octagon on line 16. When you review the you know what? I feel like I personally don't need to go over debug information. I think personally I can skip this part on account of I have a left debug handy, and this is technically a review for me, and I still have this much of this book to try to get through before the 5th of December. Okay, just a reminder, if something gets blocked, it's staying blocked. So if you're referring to something that got blocked, I don't have any information because that's going to stay blocked. So maybe you should rethink what you try to paste in people's chats. Hello, Rahit S. Alright then. Chapter 4, Traveling About the Stack. This chapter moving about the stack, how local variables are stored, viewing threads, tracing through assembly code, viewing the memory. Debuggers can be powerful things. They can leap tall computer applications in a single bound and see through them to find all their flaws. The more you know about these little debuggers, the more you can put them to use. In this chapter, we show you how to move about the stack and make use of advanced debugger features. Stacking your data. A stack is a common thing in the computer world. We have stacks of bills and stacks of paychecks and stacks of data. The stacks of data are interesting because unlike bills and paychecks, they live inside the computer's memory. But the stack metaphor is appropriate. When the operating system runs an application, it gives that application a stack, which is simply a big chunk of memory. But the data is stored just like a stack of cards. With a stack of real cards, you can put a card on the top and then another, and do that 6 times over. Then you can take a card off and take another card off. You can put the cards on the top and take them off the top. And if you follow these rules, you can't insert them into the middle or bottom of the stack. You can only look at what's on the top. A stack data structure works the same way. You can store data in it by pushing the data onto the stack, and you can take data off by popping off the stack. And yes, because the stack is just a bunch of computer memory, sticking around accessing memory in the middle of the stack is possible. But under normal circumstances, you don't do that. You put data on you put data on and take data off. Technical stuff. What's interesting about the stack is that it works closely with the main CPU, such as the Intel, Pentium, or AMD Athlon 64, or whatever is inside your computer. The CPU has its own little storage bin right on the chip itself. It isn't in the system memory or RAM, it's inside the CPU itself. Works gaming, I bet a lot of things are quite challenging for you, including not being a rude person. This storage bin holds what are called registers. One such register is the stack pointer, called the ESP. It stands for Extended Stack Pointer, consisting of 32 bits of 64 bits. Because the earlier Intel processors had only a 16-bit stack pointer, or SP, when the folks at Intel replaced the earlier chips with newer, more powerful chips, they made the registers bigger and stuck on the letter E for extended to denote the bigger registers. The stack is useful in many situations and is used extensively behind the scenes in the applications you write. The compiler generates code that uses the stack to store local variables, function parameters, function calling order. It's all stacked onto the stack and stuck in place, ready to be unstacked. Moving about the stack, the code blocks debugger, like most debuggers, lets you look at the stack, but really you're not looking directly at the stack. When a debugger shows you the stack, it is showing you the list of function calls that led up to the application's current position in the application code. However, that information is stored in the stack, and the debugger uses the stack to get that information. So that's why programmers always call the list of functions calls the stack, even though you're not actually looking at the stack. Figure 4-1 shows an example of the call stack window in code blocks. To see the call stack window, simply you can try viewing the stack yourself. Take a look at the nested calls example shown in listing, etc. Try out call stack window. Nope. Remember, stack features are common to almost all debuggers. We won't say all because we're sure that some truly bad debuggers that don't have stack features are out there. But the good debuggers, including those built code blocks and Microsoft Visual C++, include features for moving about the stack. Tip: debuggers use different terminology for the window that shows stack information. Borland C++ Builder and Borland Delphi, a Pascal tool, both use the term call stack, just like code blocks. To open the call stack window in C++ Builder, choose View Debug Windows Call Stack. The Inside Debugger uses the term stack window. You access it by choosing View Stack. No matter what particular product calls the window that contains stack information, the essential functionality is the same. To show how you arrived at a particular point in the code. Storing local variables. As you get heavily into debugging, it always helps to fully understand what goes on under the hood of your application. At this point, we'll speak on two levels. One level is your C++ code, and the other is the resulting assembly code that the compiler generates based on your C++ code. Assembly is the human-readable form of machine code that your processor on your machine understands. Throughout this chapter, we clearly state which level we're referring to. Suppose that you write a function in C++ and you call the function in another part of your application. When your compiler generates an assembly code for the function, it inserts some special code all at the beginning and at the end of the function. At the start of the function, this special code allocates space for the local variables. At the end of the function, the special code deallocates the space. This space for the variables is called the stack frame for the function. This space for the local variables lives on the stack. The storage process works as follows. When you call your function, the computer pushes the return address onto the stack. After the computer is running inside the function, the special code that the compiler inserts saves some more of the, the stack space, just enough for the variables. This extra space becomes the local storage for the variables, and just before the function returns, the special code removes this local space. Thus, the top of the stack is now the return address. The return then functions correctly. Technical stuff. This process with the stack frame takes place with the help of the internal registers in the CPU. Before a function call, the assembly code pushes the arguments to the function onto the stack. Then it calls the function by using the CPU's built-in call statement. That's an assembly code statement. This call statement pushes the return address onto the stack and then moves the instruction pointer to the function address. After the execution is inside the instruction pointer, after the execution is inside the function, the stack contains the function arguments and then the return address. The special function startup code called a prologue saves the value in one of the CPU registers called the extended base pointer or EBP register. Where does the prologue save the value? On stack. The prologue code first pushes the EBP value onto the stack. Then the prologue code takes the current stack pointer, which points to the top of the stack memory and saves it back in the EBP register for later use. Then the prologue code adjusts the stack pointer to make room for the local variable storage. The code inside the function then accesses the local variables and offsets above the position of EBP on the stack and the arguments as offsets below the position of EBP on the stack. Finally, at the end of the function, the special code, now called an epilogue, undoes the work. The epilogue copies the value in EBP back into the stack pointer. This deallocates the local variable storage. Then it pops the top of the stack off, as opposed to below the top of the stack off, and restores this value back into EBP. That was, after all, the original value in EBP when the function started. Now the top of the stack contains the function return address, which is back to the way it was when the function began. The next assembly statement is a return, which pulls the top of the stack off and goes back to the address that the epilogue code pulled off the stack. Just think, every single time a function call takes place in your computer, this process takes place. Kind of gives you a newfound respect for that big pile of bits and bytes, doesn't it? Technical stuff. Inside the computer, the stack actually runs upside down. When you push something into the stack pointer goes down in the memory. It gets decremented. When you pop something off the stack pointer gets incremented. Therefore, in the stack frame, the local variables are actually below EBP in memory, and you access their addresses by subtracting from the value stored in the EBP register. The function arguments in turn are above the EBP in memory, and you get their address by adding to the value stored in EBP. Technical stuff. The one topic we didn't discuss in the preceding technical stuff paragraph is the return value of a function. In C++, the standard way to return a value from a function is for the function's assembly code to move the value into the extended accumulator or EAX register. Then the calling code can simply inspect the EAX register after the function is finished. However, if you are returning something complex, such as a class instance, things get a bit more complex. Suppose that you have a function that returns an object, but not a pointer, as in the function header my class, my function. Different compilers handle this differently, but when the GCC compiler that's a part of CodeBlock's C++, MinGW, or CYG1 encounters something such as my class inst equals my function, it takes an address of inst and puts it in EAX. Then, in the function, it allocates space for the local variable, and there's in the return line, it copies the object in the local variable into the object whose address is in EAX. So when you return a non-pointer object, you are, in a sense, passing your object to the function as a pointer. Debugging with advanced features. Most debuggers, including CodeBlocks, have some advanced features that are handy when tracing through your application. These features include the capability to look at threads and assembly code. I'll just briefly just look back, make sure I didn't skip anything important in the debugging. I think it's all the usual things. Well, this is good. Okay, I can mention that part. Hold on. Okay, there are some things I could mention about debuggers before I move on. Okay. Recognizing the parts of the CodeBlock debugger. The CodeBlock debugger, the reason I mention this is because it's not just their debugger, there's other debuggers that have similar things. The CodeBlock debugger displays the debugger toolbar whenever they debug an application. The previous sections of this chapter discuss many of the buttons in the debugger toolbar. Debug, continue, next line, next instruction, step into, step out. However, debugger contains a number of other interesting buttons you should know about. Sometimes you can examine a piece of code in the editor and want to see what the variables look like when you get to that point. To see what happens, place the text cursor to the place you want to stop. Hovering the mouse cursor over the place you want to stop isn't enough, and click Run to Cursor, the second button on the debugger toolbar. The debugger stops at the line where the cursor is resting. In this case, the text cursor acts as kind of a breakpoint for the debugger. After you debug your application for a while and locate problems you want to fix, you may not want to run the rest of the application. When this situation occurs, simply click Stop Debugger, the button that looks like a box with an X in the middle. The debugger stops immediately. You can make any required changes and restart the debugger as normal. CodeBlocks provides access to a number of debugging windows. In fact, you can see one of these windows previously in this chapter, the disassembly window. You access these windows by clicking debugging windows. I'm going to skip that. I'm going to move on to this part. Debugging with different tools. You can use several tools for debugging your code. However, which compiler you usually use dictates which debugging tools you can use. For example, Microsoft Visual C++ is a really good debugger, but getting it to debug an application compiled with Dev C++, for example, is difficult because different compilers use different forms of debugging as simple information. The type used by the various breeds of GCC compilers is different from the type used by Microsoft Visual C++. Standard debuggers. Here's the quick rundown of some of the debuggers that are available. Visual C++. This debugger works similarly to code blocks debugger. It's primarily for debugging applications that were built by using Visual C++. However, if you are brave and need to debug something for which you have no code or similar information, its support for assembly code debugging is good. GDB. This is the standard debugger that ships with MinGW and CYG Win. It's a common command line tool, but we don't recommend using it as such. Instead, we suggest using the Insight debugger with it so that you can use a graphical front end. This makes life a lot easier, but if you insist on using the command line version, you can learn about it by typing GDB at the command prompt and then typing help. Dev C++ 5. Starting with version 5, Dev C++ has an integrated debugger that works similarly to the Insight debugger. You may want to give this a try. If you're using the version of Dev C++ prior to 5.0, you have to use the Insight debugger. Okay, great. That's pretty much everything. So then okay, great. Just a few more pages and I'll be in the next book, which is book 4. Yay. Okay. Debugging and advanced features. Most debuggers, including C++, have some advanced features that are handy when tracing through your application. These features include the capability to look at threads and assembly code. If you are writing an application that uses multiple threads and you stop at a breakpoint, you can get a list of all current threads by using the Running Threads window. To open the Running Threads window in the main code blocks window, choose Debug. Debugging Windows Running Threads. A window showing the currently running threads opens. Each line looks something like this. You know what? I'm not too worried about that part. So tracing. There's assembly code. If you feel the urge, you can view the actual assembly code. The only time you ever do this is when we have this and we absolutely must get down to the hardcore nitty gritty. Okay, so code blocks, let's do that. Cool. Some readers have noted that the window, okay. Basically anything that's like here to code blocks, I'm just no. So I'm not actually going to use that because I have my own preferences of things. Okay, so since I'm kind of just going to not bother with that, then that means we're now into book 4 of 6. Woo! And on that note, this is an excellent time. Ooh. Okay, I'll preview a bit about the contents for book 4. So book 4 is advanced programming, and the contents at a glance are the following. There's chapter 1, working with arrays, pointers, and references, and the sections of that are building of arrays, pointing with pointers, and referring to references. And chapter 2 is called creating data structures, and those sections are working with data, structuring your data, naming your space. And then chapter 3 is called constructors, destructors, and exceptions. So the first section is called constructing and destructing objects. And the second one is called programming and the exceptions of the rule. The chapter 4 is called advanced class usage. The first is inheriting correctly. And the next is using classes, types, then classes. And then chapter 5 is creating classes with templates, and that includes a few sections. They are the following: templatizing a class, parameterizing a template, type defining a template, deriving templates, and templatizing a function. Now that's going to be a good review for what I learned last year when I was taking advanced object-oriented programming and working a lot with C++ to handle the projects in that class. Chapter 6, programming with the standard library. These include these sections: architecting the standard library, continued classes, the Great Container Showdown, copying containers, creating and using dynamic arrays, working with unordered data. Chapter 7, working with lambda expressions. That would be good to get a review on that. Also, creating more readable and concise C++ code, defining the essential lambda expression, developing applications with lambda expressions. Right, so then that's going to pretty much do it for tonight's reading. And additionally, it's almost 10 o'clock, so I think I'm going to cut out the stream like real soon. Yeah. That's pretty much it for this evening. Crazy busy week, and today was pretty busy also, so the fact I'm even awake right now is kind of I don't know why. I'm very tired, but now I'm gonna go get some sleep. That sounds like a plan. Well, alright. Thank you so much for everybody who came by, even if some people were even just rude and trolly. Thank you. Maybe someone will check this out in the future, in which case, awesome. In the meantime, I'm going to be heading on out to Dreamland. So, whatever's going on, whatever time it is day for you, just make the most of it. And I'll be trying to do a stream tomorrow. Maybe some dancing, maybe some C++. Maybe both. I don't know. We'll see. The C++, not the coding. Not yet. Art time, if I feel like it. We'll see. I don't know. But yeah, just if you're interested, see my YouTube. I've got the shorts. That's mostly all about improv dance. I have some lives. That's mostly about C++ All-In-One For Dummies, which this is one of. But also there's occasional improv dancing that I put in on the lives. If you're at all interested in random dancing fun times, I also have that going on over at TikTok, which is also Becky828. I just recently started back trying to do some things with Twitch, as far as random dancing time, stuff like that. And I'm looking forward to continuing on my playthrough of Kingdom Hearts 3 Critical Mode sometime in the near future. I don't know about tomorrow though. Depends on how things go with getting sleep tonight and all of that wonderful stuff. So yeah, that's kind of pretty much do it for this stream. Twitch is also Becky828. I also have a Patreon. Also Becky828. There's nothing going on as far as a paid thing. It's free. It's just a hub sort of deal. I need a hub sort of deal is my thinking, since I'm trying to do all these different things. I also have a Tumblr, also Becky828. Looking forward to starting some art time. Haven't done any drawing in a while. That'd be good. So anyway, thank you so much for checking everything out. Those of you who are kind enough to in real time or on demand, it's possible. Again, whatever your morning or evening, whatever kind of time of day you're dealing with, just make the most of it. Thank you so much. Bye-bye.